Hello everyone, my name is Avant Mehta and today I'm working on ABE425 Lab 8, which is the Fourier series and the Fourier series app. So the way I'm going to go about my video for today is first I'll give a brief introduction to Fourier series, and then we'll have a look at how I was able to use the concepts we learned in class to match onto three different waveforms. So let's begin with the introduction. The Fourier series analysis of signals comprises a stepping stone towards the Fourier transform, which is actually the cornerstone of signal processing. The principle of Fourier series is that any signal, even the ones with discontinuities, can be written as a sum of sine and cosine waves of varying frequency and varying amplitude. So in this lab, we're dealing with a discrete case of the Fourier series where we define the input functions on the interval from 0 till 2 pi. That being said, let's get into the app. So here you can see I have the approximation for cosine and approximation for sine, the sine and cosine spectrums, and the orthogonality check for each of the cosine and sine. And there's three parameters we're using today. The NR basis, that tells us how many forms or how many bases we're going to use. The waveform, which can be square or saw or triangle. These are the ones I've programmed for the use today. And the functions can be Fourier or sine. I'll get to that when we get there. So first, let's have a look at a basic example of a square waveform, as you can see in both the diagrams for sine and for cosine. If you look at the cosine spectrum, you'll notice that it's in the order of 10 to the minus 4, which means that these are actually mathematically meant to be all 0, but just by the approximations while calculating the values close to 0, they don't end up being exactly 0, but that's what it mathematically is. The really valuable stuff happening here happens in the sine function, because we can approximate using only the sine functions. And we do a really good job in being very close to the square wave all the way across, using just 10 bases. So this is an odd function, because if you look at the sine spectrum, you'll see that only the values or the coefficients of sine with odd numbers have values over here, but not even numbers. And also worthy of note is that the magnitude for each one goes in somewhat exponentially lower, starting from about 1.3 and already heading below 0.25 as we reach the ninth value. And then we have the orthogonality check for the cosine and for the sine. And what we're calculating here behind the scenes is A transpose A to the negative 1. And that means that for an orthogonal function set, which is what we're testing for, only the values on the diagonal will have any values that are not 0. So to check that we have a diagonal matrix, we do the orthogonality checks for these two. Now let us change the NR basis down to 3. And as you can see, it becomes much worse at approximating the function all the way. But even then, it does a good job with NR basis of 3. I can change the value to something pretty high, like 80. And as you can see, it does a really good job for the straight parts of the square wave, but it has these jumps over here at the discontinuity. So I'll change this back to 10. And now I'll change the waveform from square to saw. And I'll refresh this so we can see what's happening. And as we can see again, the cosine values are all 0. Again, they're in the order of 10 to the minus 4. So mathematically, they're supposed to be 0. And the sine waves do a good job with approximating this saw wave all the way through. But over here, it's not really either an odd or an even function, because all the integer values of the sine coefficients have values and it alternates. So it's not like half of them are 0. And again, the orthogonality check is passed because it shows up as a diagonal matrix. Next, we'll change this to a triangle waveform and we'll refresh. And over here, the sine values are all mathematically equal to 0. They're in the order of minus 16. And the cosine value has one value which is very high, the very first one, 1.27. and the other values are much less than 1. Actually, it's something like 0.14. So that concludes my work in demonstrating my app. Now let's move on to the questions that I had to answer for the day. First up, we have the basis functions of a Fourier series form an orthogonal set. What does this mean, and how can you tell from the plots? So let's recap a bit. We have our orthogonality checks over here for cosine and sine. We know that for an orthogonal function set, only the values on the diagonal will have values and the remaining values will be 0. So that's actually why we have these checks in the first place, to make sure it's flat everywhere else except on the diagonal, and that's why it spikes like this. And of course, that's to check that we have a diagonal matrix. That's how we can tell from the plots over here. Our second question was, explain why in the case of the square wave signal, the coefficients for sine basis functions have values, whereas the coefficients for cosine basis function are essentially 0. So for that, let's have a look at the sample square wave over here, such that it has the value positive h from 0 till pi, and it has the value negative h from minus pi till 0, and continues like this, so on and so forth. If we use the function cosine x and apply it over here, alongside the square wave function, we see the net area must be 0. As you can see, this area here from pi till minus half pi is the same as from minus half pi till 0. And because the net area is 0, we know that the value of a1 must be equal to 0 for the cosine coefficient. And if you look at a2, extending the idea using the function cosine 2x across the same square wave, we see again the net area is going to be 0. And if we extend this idea further a little bit, we lead to the conclusion that all the an values are going to be 0 for the same reason. And that's why all the cosine coefficients will be 0, or essentially 0. Of course, it's because the calculation errors, it's not exactly, but mathematically it's going to be 0. And the third question we have is, in the case of the square wave and the triangular signal, even for a large number of basis functions, it is not possible to obtain a perfect approximation at the flanks. What is the name of this effect? And that's the Gibbs phenomenon. As you can see here, the Gibbs phenomenon is the peculiar manner in which the Fourier series of a piecewise continuously differentiable periodic function behaves at a jump discontinuity. And that ends my lab for the day. As always, thank you so much for watching.